Okay, so let's talk some more about gravity. So we've talked about free fall. I'm going to expand on that a little bit today and talk some more about how free fall and orbit are related, and the whole idea of gravitational fields. So a little bit of history about gravity. Gravity's always been around, but it wasn't really until 1665 that Newton started thinking about gravity. So you might have heard of the bubonic plague. Really? Oh yeah, we'll get it. Never mind. I'm not. Thanks. We're ready for it. So in the mid-1600s, there was this thing in Europe called the Black Death. The plague, the bubonic plague, was spread by rats. And so they closed a bunch of universities and schools down. And so Newton, rather than go to Mexico like all his friends did for spring break kind of thing, he went home. He didn't do that. He began thinking about gravity. Now, you know the whole story about Newton probably getting hit in the head with an apple, right? That's kind of the myth. Probably never happened like that. I can't imagine Newton would be standing under an apple tree and get bumped in the head. Likely saw an apple fall on a walk, is what the sort of the scientific thought is. A century before him, a gentleman by the name of Johann Kepler developed laws to explain the motion of the planet. So if you look up in the night sky, the planets are the really bright stars that don't appear to, that do appear to move. They tend to wander through the constellations. That's where the word planet comes from. It's the Greek word planetos, which means to wander. Anyway, so Kepler came up with these mathematical reasons or laws to explain the motion of the planets. And Newton wondered if the same force that caused an apple to fall to the ground from a tree. He wondered if it was the same force that was causing the moon to fall, causing the apple to fall, causing the planets to move. And of course, he was right. So this led him, math, thinking, came up with what's known as the law of universal gravitation, which states, and you don't need to write this down, you just need to be aware of it, or at least summarize it if you want. Between every two objects, there exists a force of attraction. Did I make the joke about how I'm attracted to the pencil sharpener? Yeah. I made that joke, right? I'm attracted to the pencil sharpener.
Oh, yeah.
I made that joke.
That's not funny.
No. I'm also attracted to the first aid kit over there, but not as much. How come? It's what? It's not sticking to me. Oh. I guess. It's also farther away, right? The farther something away is, the less attractive it might be. And this force is proportional to the product of their masses. I am far more attracted to the bookshelf than the first aid kit. How come? Bigger. It's got a greater gravitational... Now, okay, all joking aside, am I physically, gravitationally speaking, attracted to the bookshelf? I am. So how come I don't go slide over to the bookshelf? Well, it's not that big of an attraction. You're right. It's not really that big. Not only that, but there's things over there, like I'm attracted to that wall as well, right? So while I'm being pulled this way, I'm being pulled this way as well. Okay? So this force is proportional to the product of their masses. In other words, bigger masses have a bigger gravitational pull, and inversely proportional to the square of the distance between their centers. So in other words, the farther are they away, the less that attraction is. Okay, so that's Newton's law of universal gravitation. And in equation form, it is F equals big G m1 m2 all over r squared. Okay? Now I will say that there will be no problems that have that formula in it. Okay? You don't need to solve the universal gravitation problem. That's a grade 12 concept. Okay? But having said that, I'd like you to think about the value of G. So M1 and M2 stand for the masses. So like here's like M1, I guess red on red doesn't work. M2, right? The bigger the masses, the more the force. And the greater the radius or the distance squared, the less the force. So is big G going to be a really, really big number? Or is it going to be a really, really small number? Why do you say small, Jason? Well, remember I said, what is that force of attraction between me and the bookshelf? Is it big or is it small? It's pretty small, right? So that attraction is actually seen here in this. If you wanted, you could measure that distance. Approximately how far is it between me and the bookshelf? 6 meters maybe, something like that? 6 meters. My approximate mass, about 500 pounds. Well, even if you assume I'm 200 pounds, right, which is approximately 100 kilos, give or take a little bit, I'm a little less than that, so let's just say 75 kilos. Now, what do you think the mass of the bookshelf is, including all the books?
Heavier than you.
You think so?
Yeah.
Okay, how about 100? So 75 times 100 divided by 36 is the force of attraction. Multiply that out for me. Over here, come over here. 75 times 100 times 100, and I'm divided by 36. So that's like 20,000 newtons. But I've forgotten about what? 20,000, I forgot about the big giant G. And G is a really, we know that this force of attraction is pretty small, so big G must be a really small or big? Small number. In fact, its number is 6.67 times 10 to the minus 31. So if I take that 20,000 and I multiply by 6.67 times 10 to the minus 31. You're not getting it. About 1.4 times 10 to the minus 26 newtons. 24 zeros, 1. That's the force of attraction between me and the ocean. So it's pretty tiny. Okay? Okay. Now, here's where you might want to start jotting some things down. This is sort of stuff to write down, important stuff. The region around a mass in which a second mass will experience a gravitational force is described as a gravitational field. That's a definition that you're supposed to know. Gravitational field. All objects have a gravitational field. The big counter at the top here, gravitational field. Jason has a gravitational field. The fan over there has a gravitational field. The wall. The box up on the shelf. Oh yeah, I gotta take the batteries. Everything in the room has its own gravitational field. And it surrounds that object. The strength of the field in any place is defined as the gravitational force that a unit mass, a 1 kilogram object, would experience if placed there. This strength is represented by the letter G. Okay, so that is the strength of the field. It's how much force would an object experience at that, right, that point, that 1.0 times 10 to the minus 26. That's the gravitational field strength here. Who's grade 12's in the room? Vinny, right? Oh, there's more than I realized? Okay. This is important too. When a gravitational field is drawn, the field lines are closer together where it is strong. Where it is weaker, they are further apart. So they sort of look like vectors, but they're not. They're called field lines. I'll let you jot that down, then we're going to draw them. Pretty sure that. Okay, so that means that it kind of looks like this. This is a diagram of the Earth's gravitational field. Right, there's the Earth. Colby, all right there? You having a puck battle or something or other, or what's going on?
Yeah.
Feeling a little oh, yeah. That's no good. So this is a picture of the Earth's gravitational field. And where they are close together, here it is strong because they're closer together. And where they're further apart, up here, they are weaker because they're further apart. Now, if somehow some James Bond supervillain was able to increase the Earth's gravitational field by 2, what would the diagram then look like? What would happen? For the lines to be, well, for it to be stronger, they'd have to be close together. Well, the only way I can make it close together is if I made more lines. Right? So if this Bond supervillain was able to do that, then that would mean that the lines would be like that, close together. Right? So again, it's not the length of the line like a vector that matters, it's how close it is to its neighbor. Okay, does that make sense? Give me the nod of agreement.
Yes.
Okay, now, this diagram implies that gravity is weaker as you climb in altitude. Here we are on the second floor. Are we further away from the center of the Earth than the students down below? Yes. Technically, you're a little bit lighter up here. You're farther away from the center. And when I jumped up on the counter yesterday, I was even lighter. By how much? Negligible. Hardly anything.
So if you weigh yourself on top of the counter compared to downstairs, you'll weigh lighter.
Slightly, but not with that kind of thing. You would need a super sensitive scale. Right? And there'd be lots of variations, right? Like, even if there was like any particles that fell on me that I didn't notice, even like a piece of paper could be on my shoulder, and it would, right? So yeah. But it does imply that gravity is weaker as you climb altitude. Now, there's a reason that I talk about this, because if you were to graph a graph of gravity at different altitudes, it would appear something like this, right? As you go up in altitude, this is gravity, the gravity goes down. As you go up in altitude, the gravity goes down. Okay, I'm just going to put that over there for the time being, get that out of the way. As you increase in altitude, gravity goes up, or gravity goes down. Top of Mount Everest, they weigh less. Right? Unfortunately, there's not much oxygen, so that's kind of a hindrance. Say again? Hindrance? It's like something that resists you. It's a problem. Right? Like if you're blind, that's a hindrance to playing in the NBA. Okay, so now I want you to notice that at an altitude of about 400 kilometers, right here, gravity still pulls at about 9.5 newtons per kilogram. What is it here on Earth? 9.8. You go up 400 kilometers, which is about Space Shuttle, ISS, International Space Station altitude, still gravity of about 9.5. Well, now hold on here. You guys ever see the Chris Hadfield sketch, or the Chris Hadfield? I'll start again. Chris Hadfield video where he's playing guitar up in space there. He's a Canadian guy who's the commander of the International Space Station, right? Is he floating around up there? Aren't they weightless up there? They're floating around. You've seen those videos, haven't you? Where they're playing around with the water and tossing food at each other. What's that? But how? Like gravity's only gone down from 9.8 to 9.5. That's all it takes to be like floating around. 9.5, you can float around. Really? What's the gravity on the moon? Anyone know? What's the number? Average, you know? 3.2, you're close. Less. 1.6. Gravity on the moon is 1.6. Remember the video yesterday, Wayne, where the guy the astronaut dropped the hammer in the feather? How come it fell so slow? Because there's less force, it's less gravity. Like if I were to drop my screwdriver on the moon, it would go. It'd be very freaky. You know what? I'm going to show you guys the coolest thing you've seen in a week today. Remind you, Jason, don't let me not do it today. Okay? Well, I better not do it right now because it will just cause too much disruption. But you can actually make things fall a lot slower on Earth. But up in the space shuttle, gravity is only 9.5. That is not enough to make things weightless. So how do they do it? Is it all a big hoax? No. Here's how it works. The space shuttle astronauts, and I wouldn't bother writing anything down just yet. Just listen, let me explain, and if you want to write it down later, you can. Space shuttle astronauts and anything else in orbit are actually falling forever. Falling forever. If I were to strap my nerd scale to my feet and jump off the CN Tower, what would the scale read as I plummet to my death? Zero. I'd have achieved weightlessness. Am I really weightless? Or just sort of appear to be weightless? I can't really measure my weight as I'm falling. Now, my fall from the CN Tower would take about maybe 8 seconds, max. Right? But if you could somehow fall forever, well then that zero weightless feeling would last, well, forever. So how can you fall forever? Well, this is how. They just never land. How come? Because the shuttle is traveling at a great horizontal speed. So if I take my crazy Mr. Pac-Man, right, and if I just drop it, well, it falls, right? And if I throw it sideways to Hunter, eventually it falls like that, right? And if I can throw it even faster, if I can throw it even faster, it doesn't fall as much, right? If I could throw it even faster, I could maybe actually get it to go. If I was really, really tall and stood on a big counter, I could throw it far enough that it might land there, which would be like sort of like around the corner of the Earth, right? Not the corner, but you know what I mean? It would go around the curvature. And if I could throw it even faster, well, eventually when it gets to there, guess what? It just keeps doing what? Going around. It keeps orbiting. Let me get this out of the way. Right? Yeah, does that sort of make sense? You throw it so fast sideways, right, that it matches the curvature of the Earth. And then it just keeps doing what?
That's messed up. Does that actually happen?
Yeah, it's happening right now. Look up in space. All those satellites are doing that. All those satellites are going so fast horizontally that they're falling around the corner, matching the curvature of the Earth, and that's called orbiting. Now, if they don't go fast enough, what happens? They come crashing to Earth. Now, that actually happened back in the late 80s, I think it was. There was a space station. Just put it there in the corner there. The U.S. put up a space station called Skylab back in the 70s, and it came crashing to Australia sometime in the late 80s, I think it was. Okay? What's that? I don't know. Did they come crashing there?
They were supposed to come crashing down this summer.
Oh, is that right? I'll have to wear a helmet. To be sure. Right? So that does happen. Now, what happens if your speed is so high? What if it's even more? What's going to happen? Well, your orbit's going to get bigger and bigger and bigger, and eventually you're going to be away from gravity and away you go. You're not.
These are the only ones you have.
Oh, yeah. Oh. I took 4 of this today, yeah. There might be a couple downstairs. Hopefully. Okay, we'll see. The vector sum of the horizontal motion and gravity causes the shuttle to orbit the Earth at high speed. Since gravity is constantly pulling down on astronauts, they are in constant free fall. They are constantly falling, which is, just like me jumping out of the CN Tower, a state of what we call apparent weightlessness. That's not when your mom loses weight. Get it? Apparent.
Yeah.
I guess it could be your dad. Now, they're not actually weightless. They actually do have a weight. We just can't measure it. Do you actually lose weight? Is the force of gravity less than you when you jump out of the CN Tower? No. You just can't measure it because anything you have to attach to yourself to measure your weight is also doing what? Falling. That's exactly what's happening in the space shuttle. They are falling constantly and orbiting. So everything just kind of hovers there. So it is not because there is no gravity. It's because they are constantly falling. Okay, so what I've done is I've created a little clicker quiz that goes with this video. I've provided you the questions now. So if you want, we're going to watch video. If you want to make your answer as you go, and then when we're done, you can just enter it. So want to do that? Because that way you can you'll get a better mark.
Yeah.
Which I know is really important. No?
The rock.
Well, let's see how you do. Question number 1. An orbiting astronaut would feel like they were floating in a swimming pool, on a roller coaster, about to take a huge dive, hanging from a rope, lying down on a waterbed. You guys even know what a waterbed is?
Yeah.
Back in the 70s, they thought it'd be cool to fill like a big plastic bag full of water and people sleeping on it. Couldn't get signed in?
It says it's there, but then when you see
Question number 2. Oh, they're individual. Should we do them individually? I guess we have to if they're individual, right? I guess we have to. Okay, so I say the answer is B. On a roller coaster about to take a huge dive, right? That sort of just leaving the edge feeling. If a person has a rock and lets it go, what direction will it go? Okay, this one we should all get right. Right? Maybe it's not so easy. Up, down, sideways, it will hang there like the slinky. It depends on how fast the person is traveling. Oh. That isn't an option. Jason, what's the quarterback for Seattle? Quarterback for Seattle. Cam Newton? No, Russell Wilson. The answer? E. Because if you're running with the rock, I won't run, I'll just walk. But if I'm going like this and I drop the Pac-Man, what did he do? He didn't just fall straight down, did he? Did you see that? I'll do it again. I know you guys don't have a good angle on it, right? But Anna probably has the best angle. Right? If I let go right there, what did it do? It went like that. It didn't go straight down. It turned. Now, the reason I asked where to go. The reason I asked Jason was because I just saw this on the sports highlights this morning. And I can't spell very well. Did anyone watch this football game the other day or see this in the sports? Question number 3. When a satellite is orbiting the Earth, it doesn't hit the Earth because satellite is orbiting. You know, your GPS ones. It doesn't hit the Earth because it's too high to be affected by gravity, too small for the Earth to affect it. It would hit the Earth, but it keeps missing. It uses a rocket to stay in orbit. I'll be able to just put it. You're gonna see it first. 2 more. Come on, you guys. I gotta hustle now. I got distracted there by Russell Wilson. I want an answer, man. What's the answer? It is C. It would hit the Earth, but it keeps missing. How come? Because it's moving really fast? Sideways. How many questions are there altogether? 8? Okay, we're on time. Which of the following object experiences the force of gravity? An apple falling off a tree, an apple hanging on a tree, a bullet fired from a gun, a bullet dropped from someone's hand, a rock sitting on the ground, or all of the above? Which one experiences the force of gravity? Yeah, none of these were in the video, were they? But that's okay. F, all of the above. Why? Because they're all on Earth. If a ball is tossed up in the air, when does it not experience the force of gravity? When I throw Mr. Pac-Man up in the air, on the way up, on the way down, at the top, like at the peak. On the way up and the way down, all of the above, none of the above. When does it not experience the force of gravity? Oh, geez. See, that's how you say it, you guys. You don't have to. You gotta know where you are.
Oh, jeez. Oh, crap.
Okay. Sure. So is OGs. Come on, Colby, let's go, man. When does it not experience the force of gravity? And the answer is F, none of the above. Gravity is always on. Gravity doesn't know, oh, well, that Mr. Pac-Man is at the top of his path. I'm going to turn gravity off for a moment. Gravity is always on. Now, this one here isn't really a clicker one, is it? If an astronaut orbiting the Earth lets go of a rock, what will happen to the rock? And describe the path of the rock and why it follows that path. So here's the Earth. And here's said astronaut. And here's the rock. What happens to the rock? Where is it going to go?
Like that.
It's going to continue to orbit, right? Objects in motion. Oh, hold on. Objects in motion stay in motion in a straight line path.
But gravity-
unless acted upon by an outside force, which is gravity, which curbs it. Exactly. Is there one more? Ooh, gravity actually determines how most of the universe moves about. Describe how our ideas of free fall can be related to the orbits of the planets in our solar system. Extra credit for explaining why Jupiter, the heaviest, will likely end up causing Mercury to be booted out of the solar system. Oh. Well, so gravity is causing the planets to be, they're doing the same thing. They're orbiting the sun. Because Jupiter is so massive, it's actually attracting Mercury, and Mercury's orbit is sort of changing. One last one here. I'm not going to bother that one. Okay, the coolest thing you've ever seen. Hunter, jump up on that chair there, please. There's a metal tube on there. Give me the one that does, yeah, give me the other Yeah. Well, come back. You come be my lovely assistant, sir.
What the magnet?
Come on.
Hey, is that what you were demonstrating in the hallway yesterday?
No, I was something.
Mr. Bernat does that. I saw videos on
Oh, yeah?
It's like 23 YouTube pages.
Okay, so Sarah, I want you to just kind of crouch down here. And I'm just going to drop, I'm going to put a tube here. I'm going to drop, can you see the magnet? Like, can you see her? Okay, you're going to, I want you to see how long it takes for it to fall. Okay, so just sort of catch it like at your, it's not going to be in the tube, it's on the other side, right? Okay, so like that doesn't take very long at all, right? Okay, in fact, I'm going to turn the lights on so you guys can see that. Okay, so Sarah, you're going to catch it this time. I'm going to drop it in the tube, okay? Are you ready?
Yeah.
Because it comes quick. So just, are you ready? Okay. Are you ready? Because I dropped it. Okay, how come it isn't there yet? Oh, there it is. It is a magnet, but not. Is it attracted to the pole? Is it? No. Opposite magnets. What do you mean? Do you want to see what it looks like when it drops? Do you want to curl underneath, or do you want to see from on top? Hold that for a second, because I don't want to picture it. Climb up on the chair. And tell me that isn't the coolest thing you've ever seen.
That's so weird. It's like spinning around.
Anyone else?
Why?
Come and see it. Trust me, is it not cool?
It's like it looks like the tube is moving.
Looks like a tube to it.
It's just messed up. There's like nothing.
Anna's afraid. Looks like she's like, I don't know. Get my nightmares. It actually is all. It's cooler actually if you look underneath and watch it fall. You want to lie down and see. I really. Anyone else? Yeah, absolutely. It's probably better on the chair because you get more light. Yeah. Better. Oh, you've seen it. Oh, who's all seen it before? Oh, that totally sucks. That's my thing to show people.
Why does it do that?
Why does it do it? A magnet moving. If I just throw the magnet, it actually creates a electric current, but there's nothing created. But because it's an aluminum tube, it creates electric current in the tube. And when you get electric current in there, it actually creates a magnetic field. So while gravity's pulling it down, the magnetic field is actually pushing up. It's much like air resistance. So basically, you are increasing the upward resistance, and that's why it falls so low. No one else wants to come see it? Come on. Come. before we go? No? It's very cooling for the temperature. You can watch it from up top. You can probably, if I can climb up on there, you don't want to see it from down below? I can probably climb up on the counter. No? Okay, so see it down below? See there? That's disappointing. Alright, well, we'll do the word problem tomorrow.
Okay.
Alright, can you get the backup number?
We like pitch with all five of his fingers. I can go pitch me again. I was
Vinny, we're not in the locker room now.
started this year when I was there. I landed on my head and stuff, and I saw like watching stars and really packed up and on. You don't know who it is in your
Enjoy.
Enjoy.